If you are following these videos, please like, share and subscribe. We now discuss the solution of a problem from the section Algebra. This question has appeared in the CSIR National Eligibility Test held in December 2023. The problem is related to the concepts of group theory. The problem is from the part B, which is a multiple choice question which carries 3 marks. Its question ID is 704038. The given question is, let G be any finite group. G is any finite group. Then which one of the following is necessarily true? Is necessarily true? We are given 4 options. Option 1. G is a union of proper subgroups. Option 2. G is a union of proper subgroups if order of G has at least 2 prime divisors. Option 3. If G is Abelian, then G is a union of proper subgroups. Option 4. G is a union of proper subgroups if and only if G is not cyclic. Let us discuss the solution of the problem in detail. We have G is any finite group. Let us discuss the statements given in options one after the other. We first take option 1. G is a union of proper subgroups. Is it true in the general setup when G is any finite group? No. In some particular cases, this is not true. So this is not true in the general setup. Right. So what is that situation where this fails? For that we take G, the group, is equal to Z6 under addition modulo 6, where Z6 are the residual classes modulo 6, 0, 1, 2, 3, 4, 5. It is a cyclic group of order 6. Right. So let us consider the proper subgroups of Z6. The one proper subgroup is the subgroup generated by 2. It generates 2, 4, 0. It is a proper subgroup generated by 2. And the other proper subgroup is the proper subgroup generated by 3, that is equal to 3, 0. These are the only 2 proper subgroups of Z6. Agreed. If you take their union, bracket 2, that is union bracket 3, will give you only 0, 2, 3, 4. 1 and 5 it won't give you, and it is not equal to G. We see that this cyclic subgroup generated by 2 union the cyclic subgroup generated by 3 is 0, 2, 3, 4, which is not equal to G. Thus, G is not a union of proper subgroups. Therefore, our option 1 is not true in the general setup. Let us go for option 2. G is a union of proper subgroups if order of G has at least 2 prime divisors. the above example works now. What is the order of G? That is, the order of Z6 is 6. Here 2 and 3 are two prime divisors of the order of G, that is order of Z6, that is 6. But G is not a union of proper subgroups, which we have seen in option 1. So this again, option 2 is not true. 2 and 3 are the two prime divisors of order of G, that is order of Z6, that is 6. But G is, that is Z6, is not a union of proper subgroups, which we have seen in the above case. Right. Therefore, option 2 is not true in a general setup. General setup means when G is any finite group, this will not work. And option 3, if G is abelian, then G is a union of proper subgroups. The same above example works. What is Z6 plus 6? It is a cyclic group of order 6. Every cyclic group is abelian. Therefore, Z6 plus 6 is abelian. Even otherwise also, G is abelian. But we have seen it is not a union of proper subgroups. Again, option 3 is not true. The group G is equal to Z6 under addition modulo 6 is abelian, but G is not a union of proper subgroups. Therefore, option 3 is not true. Option 1, option 2, option 3 are not true, and it is a multiple choice question from the section B. Only one correct answer will be there. Therefore, the correct answer for this question is option 4 by elimination procedure. By elimination procedure, option 4 is our answer. Therefore, the answer to this question is option 4. What is option 4? That is, G is a union of proper subgroups if and only if G is not cyclic. That is option 4. That statement is true in the general situation, that is when G is any finite group, this is true. This is true. So the answer to this question is option 4. Now our students will ask the proof for this statement. That is, what is the proof of this statement given in option 4 set? Yes, we will do it in the next slide. We have G is any finite group. So in that case, G is a union of proper subgroups if and only if G is not cyclic. Let us prove this statement. Proof. Suppose that G is a union of proper subgroups, say H1, H2, Hk. That is, G is equal to the union of Hi, where union is taken over I is equal to 1 to k. What is that we want to prove? We want to prove that G is not cyclic. We prove by contradiction. Right. Assume the contrary. That is, you are assuming that the opposite of G is not cyclic. That is, G is cyclic. When G is cyclic, it is generated by a single element. Let that element be A. Let A be any generator of G. Then G is the cyclic subgroup generated by A, which is whole of G, bracket A. So, but G is equal to the union of Hi. Therefore, G is equal to bracket A is equal to the union of Hi. So, this generator A will belong to one of the proper subgroups Hi, say Hj. So A belongs to Hj for some j, right? 1 less than or equal to j less than or equal to k. And now A belongs to Hj, A square belongs to Hj, A cube belongs to Hj by closure law, doing like that. Then bracket A is a subgroup of Hj using the closure law. And bracket A is G. So G is a subgroup of Hj. This is a contradiction. Why? Because Hj is a proper subgroup of G. Hj is a proper subgroup of G. How come G is a subgroup of Hj? That's not true. So this is a contradiction. This contradiction is due to our false assumption. Therefore, your assumption is false. Therefore, that is G is cyclic is false. That is, therefore, G is not cyclic. Right. That is the one part. That is one part. So, if it is a union of proper subgroups, then G is not cyclic. We prove the converse part in the snippet. Now, conversely, suppose that G is not cyclic. Agreed. When G is not cyclic, no element of G generates G. So, for any G belongs to G, the cyclic subgroup generated by G is a proper subgroup of G. It will never be equal to G for any G. And G belongs to the cyclic subgroup generated by G, and the cyclic subgroup generated by G is not whole of G because no G is a generator. So take the union. So G is equal to the union of bracket G, where the union is taken over all G belongs to G. Then it will generate, then it will give rise to capital G. Thus G is the union of proper subgroups of G. Right. Good. So thus we have proved both the parts. Thus we have proved G is a union of proper subgroups if and only if G is not cyclic. Thus we have established the truth of the statement given in option 4. Therefore, option 4 is true. The answer to this question is option 4. That is the detailed discussion of the solution of the problem given in this examination. And it is definitely an interesting question. Right. I am sure that you have understood the solution of this problem. I wish you all the best. Thank you.